Okay, Assalamu alaikum. So today we are going to discuss how we will simulate our two-stage op-amp that we have discussed the design process earlier, how we will simulate it using LTSpice. So today we will simulate the same example that you have find the design process for it and you have did it in the previous two or three classes. So we are going to simulate it with LTSpice and see are we going to get the same values that we are expecting or no. So if we want to remember the specification that we had earlier, so we were aiming for a 60 dB gain, a 30 megahertz gain bandwidth from the supply voltage is 1.8 volt. We have a slew rate of 20 volt per microsecond and an input common mode range from 0.8 till 1.6 volt. And our load capacitor is 2 picofarad. We have a 60 degrees phase margin and we're aiming for a power consumption that should be less than 300 microwatt. So these are the values that we have found the W and L of each transistor. So for all the transistors, we are using the same length of 0.5 micron. And we have a reference current that's equal to 100 microamp. Now, again, the supply voltage is 1.8, the load capacitor is 2 picofarad, and we found the compensation capacitor of 5 picofarad. So all this, how we found these values, you should see from the earlier lectures. Today, we are just going to show how we will simulate them. So now here you can see the LTSpice page where I have placed the exact circuit that we are talking about here. So it's an exact replica there. The first thing is that we have two models of NMOS and a PMOS. And we are selecting KP, which is mu and COX equals 300 micron. The lambda is 0.01 and the V threshold of 0.49. The PMOS model, the mu and COX equal to 60 micro, lambda 0.02, and the V threshold of minus 0.51 volt. Now, if the values will be given to you different in your complex engineering problem, you can change them accordingly. And you need to make sure that for each transistor, you are calling the correct model. So if you right click on it, you can see what is the model name that you are following. So this is acting as a PMOS. And you can see that the name appears next to the transistor. Additionally, you can also change the length and the width of each transistor according to the specification that you have or your design calculation that you have did. Okay. The one important thing I want to show you is that how to give the input voltage. So we can, for the both inputs, we place a 2 voltage sources. And in the left side or in the negative side, we place a DC voltage of 1 volt. This value should lies within your range of input common mode range. In our design here, we said it's changing from 0.8 till 1.6 volts. So 1 volt is a reasonable value. For the AC amplitude, you should select it as a 0 here. Now on the positive side, you will select the same DC value that you have selected for the negative side, while your AC component should be equal to 1. Okay. Now the first thing is that after you place your transistors, all of them, and you make sure that you have given all the correct values for the transistors, the first thing is a good check to make is to check that your current mirror is working fine. So we should, since we have M8 and M5, they have the exact ratio of W over L, we should expect that they will have the same amount of current. So we have 100 microamp here, we should expect to have another 100 microamp here. While M7, since W over L is a smaller value, we expect it to be a smaller value. Okay, so the first thing is that we can do is to run our operating points. We need first to stop this one. We can stop it by adding a semicolon at the beginning, and we can remove the semicolon from here to run the operating points, and we hit the run button. Now we can see we got a sort of a table that's showing us the values of the voltages and the current at each transistor. So let's check the ID of M8. ID of M8 is 100 microamp exactly. And the ID of M5, that is lying here, is almost also equal to 100 microamp. So this is good. The current mirror is working fine. Now the ID of M7 is less than 100 microamp, and that's what we were expecting. So this makes sure that our current mirror is working fine. Now let's move forward. We can run now the AC analysis, and that we can do, but let's close operating points and we turn on the AC analysis. Now from where you are, you can bring this AC analysis is basically from here. You can click on simulate, edit simulation command, and you can select the AC analysis type of sweep selected as decade, so that you can see the x-axis as well in the log scale. We decide the number of points per decade and the starting frequency and the stopping frequency. Make sure you write mega as MEG and not just an M. It's not going to work. Okay, so now we hit again the run button, and now we select that we want to see the V out, and let's make this one bigger. And we have got two plots. The thick one, or the solid line, is for the magnitude, and the dotted one is for the phase of the V out. We can see that we are getting around, I'm reading from the values from down here, they appear. So we are getting around a DC gain of 50 dB, and unity gain frequency. So when the y-axis is almost 0, means 0 dB, we are getting the x, or the frequency, is around 3.8 almost megahertz. At the same value of this unity gain frequency, if we go to the phase plot, we can see that we have around minus 140 degree, which gives me a phase margin of 39 degrees. Okay, so now two questions come here. Why the values are different from what we have calculated or what we have aimed for, and why they are different, and since they are different, why do we suffer and then make all these calculations? Let's answer this question. The first one, they are different because the hand calculation, they are approximate, they are not exact, and they don't take care of all the complex behaviors of the transistors. Now, so they are not accurate. And why do we do them then, since they are not accurate? Because they give us a very good starting point for our simulation. Now, if you start from a random, you just place the circuit and try to plug any values of the transistor width and length, you will never, you might be able to reach to the required specification, but it will be like hit and try. There is not going to be an easy task. The point of doing the hand calculation is that they give us a very good starting point. So now we are not so far from meeting the requirements, but we are a good starting point, rather starting from a negative gain or something that's have a very small bandwidth. So we are near to achieve the required specification. So it gives us a very good starting point. And now you must start to then modify in your circuit and see what you should do in order to meet the required specification. One example is that you can do to add a resistor here, as you have discussed earlier, so that this resistor will help you to achieve the phase margin requirement that you are. So you need to go back and check what are the design equation for this resistor, and then select the correct value and place it here to check how it's going to help in achieving the phase margin requirement. And after that, you can modify slowly and check what is the effect of each transistor on the desired simulation results. After you meet all the specification and you make sure that you got what you want, you can also run transient analysis and showing that for a small sine wave, how your output is going to be magnified. You can also show the step response in order to calculate, for example, the slew rate. So how much for a small change in your input, how much your output is going to follow it. What else you can do? You can also show the power consumption calculation. So now for the complex engineering problem, what do you expect? You expect that we will give you a set of specification for a two-stage op-amp, and we expect you to show us how you calculated the value. So your hand calculation is a must, how you reach to your initial design of your transistors. And then we expect us to show us how you did the simulation and what initial specification you have got. And after that, what did you modify in order to reach the target specification? Now, it's going to take some time until you reach to the desired specification. Don't worry about that. You need to keep on modifying and checking the effect of each transistor. Now, you must make sure that M1 and M2, they should be always equal in size, M3 and M4 the same. Now, the best thing is that you can meet all the specification. If one or two are not met, then we will see what's going to happen about that. But what is more better, or the ideal situation, is that you be able to achieve all the specification with a minimum power consumption. And that will be really an excellent job to do. So now, if you have any question regarding the simulation or regarding the complex engineering problem, once it's posted, you please feel free to ask, and we will be happy to assist you. Thank you.